Hello, everyone. Today we are going to look at intermolecular forces and liquid properties.
Matter occurs in one of three physical states: solid, liquid, gas. Molecules are much closer to one another in solids and liquids than in gases. In solids and liquids, molecules touch one another, whereas in gases, they are farther apart. This is the reason why solids and liquids have much larger densities than gases. Intermolecular forces are negligible with gases, but play a significant role in solids and liquids. The properties of liquids lie somewhere between those of solids and gases. We begin the study of properties of solids and liquids by considering their intermolecular forces. We all know atoms can be combined to form molecules by sharing electrons. This is called intramolecular bonding. Intramolecular means within the molecule. Consider H2O. It changes from solid to liquid to gas. However, the H2O molecules remain intact. The changes in physical states are due to changes in the forces among the molecules rather than those within the molecules. The forces among the molecules are called intermolecular forces. There are three different types of intermolecular forces. 1. London dispersion forces. 2. Dipole-dipole forces. 3. Hydrogen bonds. In general, intermolecular forces are weak forces.
All right, to chip in here, let's look at the day-to-day example of inter and intramolecular forces. Let's consider relationship. A black man, let's say a black American, marries Latino lady. This is multiracial, right? So this is America. This is Mexico. Let's say Mexico. Let's just give an example of Mexico. It can be Brazil, can be anywhere in Latino countries. This is intermarriage. Inter. That means relationship or marriage across the border. International. Intermarriage. So this will mean that it is across the board, across the board, across the border. This is international marriage. An American marries a Latino, that is intermarriage. So intermolecular force is the forces between two different molecules, okay? Between two different molecules of the same type. Remember, this is a human, this is also human. So that is intermarriage, but different ethnic group, different background. That is intermarriage, intermolecular forces, intermolecular forces. That means is between two different molecules of the same type. Now, when we look at the intra, this is like a Latino girl marrying another Latino. They have the same tribe. They're from the same area. They have many things in common. So this is intra, within, intramarriage. That is within the same ethnic group. Like Black Americans marry Black Americans, African marrying another African, a white lady marrying a white guy. That is intra, within the same tribe. So example is when you have, I'm sure it's going to give you that same example. If you have water molecule. Water molecule has something, structure of this type, okay? Now this force, this bond between the hydrogen and oxygen is within the same water molecule. This is intra, within the same water molecule, within H2O, okay? Now, when you have another water molecule right here, let me change this. Another water molecule, something like this, right here. And there is a link between these two water molecules, between this and this. This link is intermolecular forces. All right, that is just the basic difference. Just remember using the analogy of marriage or relationship between the same tribe and between two different tribes.
This is the most common type of intermolecular force found in all molecules. London dispersion forces are the only intermolecular forces found in noble gases and non-polar molecules. Basically, these forces are electrical in nature, hence, they result in both attractive and repulsive interactions between atoms or molecules. Why and how? Nonpolar gases can be liquefied. For example, noble gases such as helium, argon, etc. can exist as liquids. These gases are made of atoms which are electrically neutral. How can gaseous, neutral atoms attract each other to form a liquid? Since these gases can exist as liquids, there must be some kind of attractive forces holding these atoms together. These attractive forces were first studied in 1930 by a physicist named London, hence the name London dispersion forces. Consider a pair of noble gas atoms. Usually it is assumed that the electrons of an atom are uniformly distributed about the nucleus. This assumption is not true at every instant. As the electrons move about the nucleus, a momentary non-symmetrical electron distribution can develop, producing a temporary dipole. This temporary dipole, in turn, affects the electron distribution of the neighboring atom. This leads to an interatomic attraction called the London dispersion force. Remember, London dispersion force is a very weak force and is significant only when molecules or atoms are very close together. These forces are actually sufficiently strong to promote the formation of solids when the temperature is so low that the motions of atoms are significantly reduced. Look at the freezing points of some noble elements. The freezing point rises going down the group. This is because the atomic number increases as we go down the group. The higher the atomic number, the greater the number of electrons, and therefore a higher probability of momentary dipole interactions. The same concept can be applied to nonpolar molecules. Consider CO2. We know CO2 exists as a gas. However, CO2 can also exist as a solid, commonly called dry ice. Consider a pair of CO2 molecules. In the first step, assume that the electrons are uniformly distributed about the respective nuclei. In this case, there is no dipole moment. As the electrons move about the nucleus, a momentary, non-symmetrical electron distribution can develop. This produces a temporary dipole moment. This temporary dipole moment, in turn, affects the electron distribution of the neighboring molecule. This leads to London dispersion forces between these two CO2 molecules. The charge distribution in a molecule can be distorted by the electric field created by neighboring molecules. The ease with which the charge distribution in a molecule is distorted is called polarizability. Thus, more polarizable molecules have stronger London dispersion forces. Larger molecules have greater polarizability because they have a greater number of electrons. In general, the strength of London dispersion forces increases with the increasing molar mass.
You can see the importance of molar mass in this London dispersion forces. Just remember that the strength of London dispersion forces increases with the increased molar mass. So that means you have to take cognizance of the molar mass when you are asked to choose which of these has a stronger effect or the strength of London dispersion forces.
Polar molecules are attracted to one another by London dispersion forces. In addition to that, they are also attracted by dipole-dipole forces. Polar molecules attract each other when the positive end of one molecule is near the negative end of another molecule.
Consider HCl molecules in the solid state. They are organized either side by side or end to end. Adjacent HCl molecules line up so that the more electronegative Cl atom is as close as possible to the less electronegative H atom of its neighbor.
This results in an attractive force called a dipole-dipole force. The dipole-dipole forces are effective only when the polar molecules are very close together. In polar molecules, dipole-dipole forces are stronger than London dispersion forces. In liquids, polar molecules are free to move with respect to one another. Sometimes they will be in an orientation that is attractive, and sometimes repulsive.
Molecules will spend more time near each other in the attractive orientation than in the repulsive orientation.
Thus, the overall effect is net attraction. In general, for molecules having approximately the same mass and size, the dipole-dipole forces increase with increasing polarity. The boiling points, as well as the melting points of polar compounds, are higher than those of nonpolar compounds of similar molar mass. In liquids, polarity has a relatively small effect on boiling point. For example, consider hydrochloric acid, hydrobromic acid, hydroiodic acid.
The boiling point increases with increasing molar mass, even though the polarity decreases.
When hydrogen is bonded to a small, highly electronegative atom in polar molecules, polarity has a greater effect on the boiling point. The highly electronegative atoms are nitrogen, oxygen, and fluorine, respectively. Between hydrofluoric, hydrochloric, and hydrobromic,
HF has the highest boiling point despite its lower molar mass.
similarly, water, molar mass 18 grams per mole, and ammonia, molar mass 17 grams per mole, have abnormally high boiling points.
The unusually high boiling points of HF, H2O, and NH3 result from the strong dipole-dipole force called a hydrogen bond.
For example, consider a pair of HF molecules. The Lewis dot structures are:
Once the H atom is bonded to the F atom, its electron becomes localized near the fluorine atom because fluorine is very electronegative.
hence, the positive side of the bond is primarily due to the proton in the hydrogen nucleus. This exposes the positive charge of the hydrogen atom. This positive charge is attracted to the electrons of an electronegative atom of the nearby HF molecule. Because the hydrogen atom is very small in size, it can very closely approach the electronegative fluorine atom. This results in a very strong attraction called
hydrogen bond.
hydrogen bonds can exist in many molecules other than hydrogen fluoride, water, and ammonia. The basic requirement is that the hydrogen atom is bonded to the fluorine, oxygen, or nitrogen atom with at least one unshared electron pair. For example, consider two molecules. The Lewis structures are. Now read the basic requirement. This molecule has hydrogen bonding.
This molecule cannot. If we compared these compounds in the liquid state, then CH3, CH2, NH2 would have a higher boiling point.
Another consequence of the hydrogen bond is the remarkable difference in the densities of ice and liquid water. Ice is a solid.
In most substances, the molecules are more densely packed in the solid state than in the liquid state. However, we know that ice floats on water, and thus it has a lower density than water.
Okay, I decided to flip back, rewind a little bit. Now, this is very interesting. Look at these two structures. Why do you think this has hydrogen bond and this one doesn't have hydrogen bond? Now, if you look at it critically, you see that there is a bond between nitrogen and hydrogen here, and there is none like that here. There are bond between nitrogen and carbon, nitrogen and carbon, nitrogen and carbon. Because when you draw this structure out, maybe let me draw the bigger structure so that you see exactly what I'm talking about. This is the expanded structure. Okay, this is nitrogen. This is the lone pair of electron. This is carbon. So carbon has 3 hydrogen on it, like that. And this is carbon with 3 hydrogen on it. And this is carbon with also 3 hydrogen, all right? So this doesn't have any hydrogen nitrogen bond compared to this. That is why this has hydrogen bond and this one doesn't have hydrogen bond. All right.
This contrast in density between ice and water can be understood in terms of the hydrogen bonding.
In liquid water, H2O molecules are close together. When liquid water freezes, the molecules have an open, ordered arrangement. This arrangement optimizes the hydrogen bonding interactions between the molecules. In doing so, it results in a less dense structure of ice compared to water. Note, a given mass of ice occupies a greater volume than the same mass of water.
Right, this is the reason why the piece of ice block floats on water, because there are poreholes, there are porous, and there are pores, spaces in between the structure of water molecule when it becomes solid. You can see the network. I can see some gaps in between. That is why ice cube will look bigger than the same amount of water and still floats on water because of the pocket of air in between them. All right, this is an interactive question. Which molecule is non-polar? All right, I want you to take your pencil and give me the answers to this interactive. I'll go back later and show you the answers. Question 2. Does CH18 have larger or smaller London dispersion forces than CH3Cl? 3. Consider the following two molecules, CH4 and CCl4. Which molecule has a larger molar mass? 4. Does CCl4 has larger or smaller LDF than CH4? And arrange these noble gases in order of increasing boiling points. Arrange them in order of increasing boiling point. That means from the smallest boiling point to the highest boiling point. Helium, argon, xenon, and neon. And finally, which of the following molecules will show dispersion forces and which one will show dipole forces? So nitrogen, Z, LDF, yes, or yes for dipole force. CH4, H2O, NH3. All right, let's go to viscosity.
Liquids, such as motor oil, flow slowly compared to water, which flows easily. The resistance to flow of a liquid is called the viscosity. The greater the viscosity, the slower the liquid flows. At the molecular level, the flow of a liquid can be described as the sliding of molecules past one another. The higher the viscosity, the more difficult the sliding of molecules past one another, or the greater the friction between molecules. Viscosity is therefore controlled by the nature and strength of intermolecular forces. As the temperature of a liquid is increased, its molecules can more easily overcome intermolecular forces. This results in a lower viscosity. In general, liquids form droplets. This behavior is due to the intermolecular forces at the surface of the liquid. Molecules at the surface experience a net inward force. This inward force pulls the molecules from the surface into the interior. This reduces the surface area. For a given volume, spheres have the smallest surface area. The inward force also makes the molecules at the surface pack closely together. A measure of the inward force is called surface tension. Note: molecules in the interior are attracted equally in all directions. Surface tension is the amount of energy required to increase the surface area of a liquid by a unit amount. Intermolecular forces that bind similar molecules to one another are called cohesive forces. Intermolecular forces that bind liquid molecules to a surface are called adhesive forces. Water placed in a glass beaker exhibits a concave meniscus because the adhesive forces between the water molecules and the glass surface are greater than the cohesive forces between the water molecules. Mercury placed in a glass beaker exhibits a convex meniscus because the adhesive forces between the mercury atoms and the glass surface are weaker than the cohesive forces between the mercury atoms.
All right, these are the two forces in a liquid, cohesive and adhesive. I think it's self-explanatory. That is why you see when you have a glass cup of water, and you see the meniscus. This is the meniscus. The curved surface of the liquid is called meniscus. So this is meniscus. So when the meniscus, this meniscus, this curves up because there is a force which is called the adhesive force. The force between this glass and the water is higher. So this goes higher, goes up compared to the cohesive force. Cohesive force is the force within the liquid. All right? The force that holds this liquid together is cohesive. The force that holds the force between the liquid and the container is the adhesive force. So if the adhesive force is more than the cohesive force within the liquid, then the liquid will rise by the side. That is why you see this water rising up by the side, because there is an attraction between the two of them. But in case of mercury, if you have opportunity of seeing the drop of mercury on the table, it looks like a ball, like a metallic ball, because the cohesive force is more than the adhesive force. So the liquid mercury tends to come together as a ball rather than attaching itself to the container or to the table. All right, that is just the difference between the two of them. All right, I'm going to pause here for clarity's sake so that you can assimilate the little one we've done here. Then we can now go to the practice section. All right, thank you.